In this video, we will look at various types of operations with Euclidean vectors. First, let's have a look at why Euclidean vectors might be useful. The most basic use of such vectors is for moving around in 3D space. With some basic vector algebra, it is possible to move to any required location in space. In addition, it is possible to extract vectors from the existing entities in the model. This gives you the ability to move relative to those entities. In many of the slides we'll use 2D examples, since it is easier to visualize. You can simply assume that the z-coordinate is 0. Also, note that in this video, when we refer to a point, we are referring to a location in space. We are not referring to point objects in Mobius. For working with vectors, most programming languages will require you to use functions. In the code example, you can see such a function. The vec_add function adds two vectors or a point and a vector. However, this video is focusing more on the general principles, not on specific functions. It is distracting to keep using the functions. We will therefore use a simple type of mathematical notation in these slides. The notation on the left is equivalent to the code on the right. In our mathematical notation, names of vectors are in bold and underlined. In addition, in the mathematical notation we do not use functions for adding and subtracting points and vectors. We just use the addition and subtraction operators, as shown on the left. When you write code, you will have to use the functions. First, we need to clarify the difference between points and vectors. They are fundamentally different concepts. Points are locations in space. For example, you might say, let's meet at the Eiffel Tower. In this case, the Eiffel Tower is a location in space. Vectors are displacements in space. For example, you might say go northeast for 4.2 kilometers. With points, it makes no sense to try to do things like addition and subtraction. But with vectors it does make sense. You can first go northeast for 4.3 kilometers. Then you can go north for 2 kilometers. You can also do addition and subtraction with a point and one or more vectors. For example, you can start at the Eiffel Tower. Then go northeast for 4.3 kilometers. Then you can go north for 2 kilometers. In this last case, it would result in a new point. A location in Paris somewhere. The key thing about vectors is that they have no fixed location. They have a direction and a magnitude. The magnitude is often referred to as the length of the vector. All the vectors in this diagram are equivalent. They all have the same direction and same magnitude. Since a vector has no location, it is often drawn at the origin. This does not mean that the vector is actually located at the origin. Drawing the vector at the origin is just a convenience. A vector can be reversed. Reversing a vector negates all of the vector components. As a result, the magnitude will not change. But the vector direction will change. One confusing thing about points and vectors is that their representation is exactly the same. As shown in the example, a point is defined by a list of 3 numbers, and a vector is also defined by a list of 3 numbers. However, the number mean different things. So in Mobius, you can still use the vec_add function to add 2 points. It will not throw an error. But in most cases, the result does not make any sense. Let's take a look at 4 of the basic operations that can be performed with points and vectors. They are addition, subtraction, multiplication, and division. We will look at each one in turn. This example starts at a point and adds a vector. It results in a new point. This example starts at a point and adds 2 vectors. It again results in a new point. This example starts at a point, adds a vector, and then subtracts a vector. It results in a new point. This example starts at a point and adds many vectors. It results in a new point. You can think of this as a chain of vectors, connected end to end. Multiplication changes the magnitude of the vector. If the multiplier is positive, then it does not change the direction. If the multiplier is negative, then it reverses the direction. Division is similar to multiplication. Dividing by a positive number changes the magnitude only. Dividing by a negative number changes the magnitude and reverses the direction. For perpendicular vectors in 2D, the vector components can simply be swapped, and one of them negated. So in this example we start with a vector 4, 2. The vectors -2, 4, and 2, -4 are both perpendicular. If you imagine walking down the original vector, then -2, 4 is on the left, and 2, -4 is on the right. Next we will look at magnitude and normalization. The magnitude of a vector is its length. The length can be equal to or greater than 0. A vector can only have 0 length if it is the 0 vector. This is where all components in the vector are 0. But it cannot be less than 0. A unit vector is a vector whose length is exactly 1. Vector normalization is the process of setting the length of a vector to 1 unit. Normalization results in a unit vector. Next, we will look at the cross and dot products. So far we looked at multiplying a vector by a number. However, we can also multiply a vector by another vector. This is what the cross product and dot product do. The cross product of two vectors returns another vector. The output vector is at right angles to both input vectors. The cross product is very useful whenever you need to move in a perpendicular direction, relative to some existing geometry. If the two input vectors are both unit vectors, then the output will also be a unit vector. If the angle between the two input vectors is 0, then the output will be the 0 vector. The dot product of two vectors returns a number. The dot product is useful for testing the direction a vector is pointing in. The number represents the length of the projection of the first vector onto the second vector. If the first vector is a unit vector, then it allows some additional conclusions to be drawn. Assuming that the first vector is a unit vector, we can say the following. If the projected length is 0, then it means that the two input vectors are exactly perpendicular. If the projected length is 1, then it means that the two input vectors are exactly parallel. If the projected length is -1, then it means that the two input vectors are pointing in exactly opposite directions.